Good morning. My name is Pablo Valdivieso Monasteris, and I'm going to present to you our paper together with Dr. George Konstantopoulos, Decentralized Nonlinear MPC for Grid-Connected Microgrids with Preview Information. Our paper centers in controllable nodes and controllable nodes, by which we mean nodes that are connected to the network but are not part of the controller itself, such as nodes controlled by different companies or similar. The loads, all of these connected with the grid through a radial topology. An example of such network can be seen in the following picture, where we have two uncontrollable sources and three controllable ones. Each of the controllable sources is connected to the grid via a three-phase inverter with an L filter. We model this using the DQ framework oriented to the D-axis of the connection voltage. The battery uses a simple integrator. Bear in mind that in these two there is a timescale difference, the battery operating at a much slower rate. Together with the inverter controllers, we have its primary controller, which is a bounded integral control that aims to regulate the power from each converter, using the drup expressions. So we integrate the drup expressions, try to drive these to zero. Some of the features of the pulse controller are the following. We have true behavior in terms of power and voltage and reactive power and the negative frequency. We can guarantee that the current is limited at all times, a fact that will be useful in the optimization problem later. The stability and tracking of power is guaranteed, and we have for the batteries a bidirectional power controller. From the network point of view, we have a simple power balance equation saying that the input from the grid and the controllable sources needs to be equal to the power drawn by the loads and the input of the controllable sources of power. The load and these uncontrollable sources of power share a common thing, that they are both exogenous signals, and in order to manipulate them properly we need to assume some things about this. The first one is that we have a measurement available at all times, and then that for the uncontrollable source of power that we have a bounded signal, and we have an n-step prediction available. Bear in mind that we allow these predictions to be different from time to time. This is to allow more freedom in how we can model the influence of external factors in the network. The next question that arises is, like, for a given node, how can we assign the power that is being generated by the uncontrollable sources of power? We do it by considering that for each uncontrollable source there is a subset of controllable sources that are connected to it, and this can be described using a convex combination. In a similar approach, each controllable source is connected to a subset of the uncontrollable sources, such that we can define these coupling neighbors. The overall goal is to obtain a power balance for each individual node, controllable node, given in terms of the input power, the power input by the grid, and the percentage of the uncontrollable power that is destined to that particular node. We have to remark that these constants are design parameters that will reflect how aggressive or how lax the controller is. A brief note on how the secondary controller operates is that we have a steady-state behavior for the power electronic devices and just the discretization of the battery dynamics, which are reflected in these two equations for x and y, respectively. These two are inputted into the distributed decentralized MPC controller that is proposed, which basically solves an optimization problem that's trying to minimize this cost based on the parameters given by the measurement of the states and the availability of the exogenous signals. The solution of such optimization problem is a sequence of reference points that are given to the primary controller. The constraints are standard, and we would like to remark here that the battery is constrained to a minimum and maximum value of the state of charge. This is to guarantee that the voltage is constant when operating in that range. This depends on the chemistry of the battery, of course. The main goal of this paper is the analysis of the recursive feasibility of this MPC controller. To this aim, what we have is the analysis of the reachable sets, because thanks to these reachable sets, we can infer some properties of the behavior of the MPC controller. We have modified slightly the definition of the reachable set to contemplate the inclusion of these disturbance sequences. A small result that we have obtained is that for a given subset of the state space, we can obtain a reachable set by computing the reachable sets of the individual ones. As we'll see later, this will be useful. Another important concept that we need to address is that the optimal operation at the steady state. This operation is important, and bear in mind here that we're only taking into account the power electronic part of the state, because the optimal operation at steady state for the battery doesn't make much sense, since an equilibrium state for the battery implies that there is no input. I mean, the input is driven to zero, which is not a suitable point to analyze. So, using the reachable sets, we can prove that the optimal operating point is an upper continuous, semi-continuous function, which has as consequences that this set, the collection of all the sets of optimal operating points, is a compact set, owing to the fact that the exogenous signals are bounded signals, and that the power imported from the grid is a compact set, lives in a compact set at least. Now, moving more into the recursive feasibility analysis, we need to define first what is the feasible set, which is basically all those states and disturbance sequences that guarantee that the input set is not empty. And we define as well a tool that will be useful later. It's called the K-disturbance tail, which essentially takes a disturbance sequences, discards the first element, and repeats the kth element. Before proceeding, we need to propose some assumptions in order to obtain stronger results. First of all, we need to assume that the deceptivity of the system is to hold. This is to ensure that the system can admit a solution. Next one is assume the turnpike property, which means that the state spends most of its time around the neighborhood of the optimal operating point. Based on these two arguments, we can deduce recursive feasibility as follows. First, we measure the state for a given disturbance sequence. We assume that this one is feasible. So, using the turnpike property, what we can say is that the state is living around the optimal operating point. So, for a perturbation in the kth element of the disturbance, we can find control inputs such that the modified sequence is a feasible sequence. which means that the constraints are not empty. Therefore, the successor state is a feasible set for the disturbance tail. The next point is to try to exploit the fact that the set of the exogenous sequences is a compact set. And how do we exploit this is just by assuming we guarantee that the difference between the updated disturbance sequence and the tail is bounded. Here we can use the dissipativity to prove that the feasible set for the updated sequence is a non-empty set, which would lead to recursive feasibility. So that's the main contribution of this paper. So some conclusions that we have proposed a grid-connected controller for a grid-connected microgrid, and we have established a rigorous analysis of the decentralized MPC controller, so we can guarantee that there exists always a solution. And we would like to remark that this exploits the fact that the controller is using both primary and secondary layers. And lastly, we would like to expand to mesh topologies and include concepts of energy pricing in the MPC optimization cost. Thank you.